Hi everyone, thank you very much for coming. My name is Semenov, and today I'm going to tell you about assortative mating and its effects on phenotypic and genetic patterns in a widespread bird species. That's it. Phenotypic differences often play a role in the maintenance of reproductive barriers. However, it's widely recognized that not all aspects of phenotypic differentiation that emerge in allopatry will then play a role as a barriers to gene flow if species come into secondary contact. And this idea is illustrated by these two mice species that first diverge in allopatry, then they come into secondary contact, and after a certain number of generations of hybridization and introgression, they lose all differences except of ear color that probably play a role in mate recognition or adaptation to different habitats. It's probably a little bit exaggerated example, but it illustrates that some traits are more important in the maintenance of reproductive isolation and potentially in driving population divergence. And hybrid zones provide perfect identification of these traits, understanding of their genetic architecture, and the forces that maintain their integrity are important for understanding speciation. And hybrid zones provide perfect opportunity to answer this question, because actually in hybrid zones, by studying patterns in the hybrid zone, we can identify traits that remain distinguished by hybridization. We can then go into the field and test what forces maintain these traits and experimentally test. And then finally, we can assess how variation in these traits is associated with genome-wide patterns, which can give insights into genetic architecture of reproductive isolation, and also it can help answer the question if factors maintaining divergent traits are the same with those that shaping genome-wide divergence. And here I apply this framework to study hybrid zone between two bird subspecies. So alba and personata are two subspecies of the white wagtail, and I sampled over 300 individuals over the 3,000 kilometer transect that spans the hybrid zone in both parental ranges. And these subspecies differ in several plumage traits, in plumage of head, wing, and back, and also they differ in the body size, and in this case, body size is a composite measure of 8 morphometric differences. And first of all, I asked if this hybrid zone is maintained by selection, and then if it is, what traits are likely under selection. And I want to tell you a little bit about how we infer processes from patterns in the hybrid zone. And first of all, we can compare the width of the hybrid zone with the model, with the prediction of a model of unrestricted hybridization and introgression that takes into account the number of generations in secondary contact and then dispersal distance. And if observed climb is narrower than predicted by this model, then it's likely maintained by selection. Also, it is useful to compare introgression between traits, because stronger selection will result in narrower climb, like in this trait 1, compared to more relaxed selection. Although many processes will affect the climb shape, and also the same climb width can be a result of, for instance, high dispersal and strong selection, or weak dispersal and very low selection. So actually, to understand what is going on, we need to see the distribution of individual traits and patterns of variance in the hybrid zone. So here are 5 scenarios with selection changing from the highest here to lowest here. And the distribution, dark gray and light gray distribution, are distribution in parental species, and then red outline is a distribution in the hybrid zone center. So if selection is very strong, it will maintain parental distribution and result in bimodal distribution of individual trait values in the hybrid zone center. If there is a small amount of hybridization, we cannot see some first generation hybrids, but some individuals will be admixed, and it will shift distributions a little bit that corresponds with bimodal with introgression model. Then, with over-selection, we can actually observe more frequent hybridization and well-defined group of recent generation hybrids that do not becross two parental species, and then, in this case, we will have trimodal distribution. Or the hybrids can backcross two parental individuals, and but it doesn't lead to complete merging of parental phenotypes, which corresponds to trimodal with introgression model. And finally, it can be a complete admixture in a hybrid swarm that corresponds unimodal model. And this continuum of selection will have corresponding change in patterns of variance, which will be highest in this case and lowest in this case. So this is what we tested for this hybrid zone. Neutral diffusion, and then differences in progression between traits, and then we modeled this different scenario using CFIT7, and then we evaluated patterns of phenotypic variance, and specifically we tested if the patterns of variance significantly differ from those predicted by scenario-free admixture. And I'm not going to tell a lot about this, and you can look in this paper or ask me after the talk. And this is what we found. So here are 4 geographic lines for head, wing, back, and body size, and lines are clients. Here is the distance along the transect, beginning in alba, and then ending in personata, and then vertical axis are trait values, and this dark shading is a variance distribution at a given distance, and here is the width of each client. So first of all, neutral diffusion client was over 600 kilometers, but for instance, head client was over 5 times narrower. Then other clients revealed surprisingly distinct patterns, and they were several times wider, and actually wing client was over wider than one expected on the neutral diffusion. And back and body size, clients were 10 to 20% narrower, but still quite close. So then the modeling of distribution revealed that head has trimodal width introgression model, and then variance is increased in 7 samples, which means that there are both parental phenotypes, various hybrids, but hybridization doesn't lead to merging of parental phenotypes. Then in wing, distribution was unimodal, no variance increased, and then back poorly fitted on any CFIT7 models, and it was no variance increase. And finally, in body size, it was unimodal distribution and only one slightly significant increase in variance. So what it tells us, it's very likely that the head plumages are maintained by selection, but it's not very clear that selection shapes other client, and if it does, it seems that selection strength is way weaker and potentially absent. So because of non-unimodal distribution in head plumages, and because plumage often plays a signaling role in mate choice, we then asked if these distinct plumages actually maintained by assortative mating. And for that, we collected data for 47 social pairs from the center of the hybrid zone, which are presented here. And then we assigned each individual to either parental alba or parental personata or a hybrid. And then we grouped these pairs in 3 categories. Same include the same phenotypes, and then near are pairs between one parental and a hybrid, and then far are pairs between 2 distinct parental. And then we use bootstrap statistics with 10,000 replicates to randomly sample males and females from this distribution to evaluate the distribution of random mating, and then we identified 95% confidence interval from this distribution and compared it with observed number of pairs in each of these 3 categories. And what we see is that there is excess of pairs in the same category and underrepresentation of pairs in far category, which means that mating is not random with respect to head plumage, and it's very likely that either head plumage itself or some tightly correlated trait that was not measured actually maintained by selection, which might explain why this client for head plumage is so narrow. And then, with respect to this finding, we then evaluated the genomic variation in the hybrid zone, and we used about 19,500 SNPs that were obtained using rat sequencing. And then, first of all, despite significant difference in all aspects of morphology, we found that it is very weak genome-wide divergence. And the first two components of principal component analysis together explained less than 2% of genomic covariance, and strikingly, most of the variation was driven by difference between this population of personata here and basically the rest of the transect, and the similar results where when we perform structure on semi-diagnostic loci, population from remote personata range was different, and then the rest was very homogeneous, and particularly note that the transition in head plumage had no correspondence transition in genotypes. So basically, the head plumage cline and genome-wide cline were very displaced in space. Interestingly, that wing bend, back and body size clines were actually consistent in variation with genome-wide cline, but not with head plumage cline. And the head plumage transition happened over population that were otherwise resembling alba like with respect to genomic composition and other aspects of morphology. And there are many cool things that can be discussed here, but the main message is that based on all sum of evidence, it seems that the factors that drive, that maintain distinct head plumages and those that shape genome-wide variation may not be the same. For instance, here is the transition in head plumage, and here is where all the transition in other trait takes place. And here is the gap in sampling, because despite significant sampling effort, we failed actually to find, to collect even a single individual wagtail because of very low population density. And second, transition in other clients closely corresponds to this area of elevation change and vegetation change. So it might be either ecological factors or demographic factors that affect position all other clients except head. So the main point I want to make here is that head plumage is very modular and varies very independently with respect to other traits, including the rest of the genome. And it's not just modular in terms of geographic variation, but there are very few intermediate phenotypes, which means that it might be very simple genetic architecture. And with respect to this finding, I want to show you there are 9 subspecies in the white wagtail, and they are very diverse in terms of plumage, but here are results of structure based on 17 microsatellite loci, and across all Eurasia, there is very little or no evidence for population structure except of this one subspecies that mostly distributed on islands and the coast. And it raises the question why such an extensive genetic diversification can exist with so little genetic and genomic divergence. So if this plumage diversification is driven or maintained by similar mechanism we found in this hybrid zone, we can expect that assortative mating is associated with a relatively small fraction of the wagtail genomes, and probably majority of genomic variation is similarly driven by demographic or ecological processes. And the main thing is that these findings raise a question about the degree to which assortative mate choice alone contributes to the process of population divergence and reproductive isolation. The patterns we observe here could be because this radiation is very recent and pretty much nothing else diverged except with this small number of plumage genes. Or actually this may have nothing to do with the age, but just because effects of selection are restricted to this very small proportion of genome, it's not sufficient to drive genome-wide divergence, and gene flow overrides these differences. And thank you very much for listening.